Part we would like to discuss with you in this lecture is the concept of constant value surfaces. In Cartesian coordinates, we already know that a point B, like the one shown here, is really the intersection of three planes. B has three coordinates, x, y, and z. And B is really the intersection of the z equal to constant plane, y equal to constant plane, and x equal to constant plane. Remember, when you say that x is equal to x1, this defines a plane parallel to the yz plane. And when you say that y is equal to y1, this defines a plane parallel to the zx plane. And when you say z is equal to z1, this defines a horizontal plane parallel to the xy plane. And if you have any point whose coordinates are x1, y1, and z1, you'll see that this point is really the intersection of all these three planes. So constant value surfaces in Cartesian coordinates, they are really planes. And every point in a Cartesian coordinate system can be looked at the intersection of three constant value surfaces. Of course, if you intersect only two constant value surfaces, you get a line here in this case. For example, if you have something like a plane x equal to x1 and y equal to y1, this means that z can take any value. So the intersection of these two planes will give you a line parallel to the z-axis, and so on. So a point in general is defined by the intersection of three constant surfaces, and here for the Cartesian case, these surfaces are planes. Cylindrical coordinates, we know that rho is the normal distance from the z-axis. So the surface defining rho equal to a constant is actually a cylinder. Every point on that cylinder has the same normal distance from the z-axis. So for when I say rho is equal to rho1, this defines a cylinder whose radius is equal to rho1. Now, when we say phi is equal to a certain phi is equal to phi1, because phi is defined as the angle between the projection of the point on the xy and the x-axis. The constant y surface here, constant phi surface, is really a plane. So I'm trying to extend that plane a little bit here. So it's a plane that makes an angle phi with the x plane. So when you intersect this plane with the cylinder, with the constant rho cylinder, you get a vertical line like this one here. So you have here a vertical line. I'm sorry, I'm trying to draw it. It's not very accurate. It's parallel to the z-axis here. Okay, it's a vertical line, the intersection between this plane and the constant rho cylinder. The last plane that we have in cylindrical coordinates is the plane z is equal to z1. Z1 can be any value. It's a horizontal plane. And when you intersect all these three planes together, you get a point P. So a point B is in general the point at which three surfaces, they are not really planes, they are surfaces. They are two planes and one cylinder. When the constant phi intersects the cylinder, it gives a vertical line. When this vertical line intersects the horizontal constant z plane, you get your point. So here the constant value surfaces are a vertical plane, a horizontal plane, and a cylinder whose axis is the z-axis. The same concept applies as well to spherical coordinate systems. We know phi is the same in both spherical and cylindrical coordinate systems. So phi equal to a constant defines a plane, and all the points in this plane, the projection, the xy plane, makes an angle of phi with the x-axis. When you say that r is equal to r1, you are saying I'm defining it's the set of all points whose distance from the origin is equal to r1. So it defines a sphere. So in this case, the constant r surface is a sphere. When you say that theta is equal to theta1, this actually defines a cone. And for theta, I have a little bit of word of warning for you. So here, for example, I'm trying to draw it in a good way. It's not coming very well. So if this is z, okay, so this point on this surface makes an angle theta, and as well this point here makes an angle theta. Okay, so the constant theta surface is actually a cone. It's a cone. Okay, And when theta goes beyond 90 degrees, the cone will look something like this. So this is a cone here. So every point on this cone again makes an angle. This will be the theta in this case. So theta is greater than 90. So this angle here is really pi minus theta. Okay, so theta does not go beyond pi. Theta is between 0 and pi. Theta does not go beyond pi. Phi is between 0 and 2 pi. And here r is a positive number always from 0 to infinity. Okay, so the three constant value surfaces in spherical coordinates are a cone, a sphere, and a vertical plane. So when the cone, as you see in this figure, intersects the sphere, it gives a circle. And when this circle intersects with the plane, it gives your point B. So again, it's a generalization of the same concept that we have seen in Cartesian coordinates. Let's take a look here at this example. There is a point given in cylindrical coordinates. It has the three coordinates 2 square root 3, pi over 3, and minus 2. So rho is equal to 2 square root 3, phi is equal to pi over 3, and z is equal to minus 2. We would like to show the three principal surfaces of this point. And we would like as well to express P in spherical coordinates. So again, the constant surfaces here, cylindrical coordinates. The first one is a cylinder whose radius is 2 square root 3 because this is rho. The phi equal to constant, phi is equal to pi over 3 is a plane that makes an angle of 60 degrees with the xz plane. Minus 2 is a horizontal plane that's below the xy plane by 2 units. And here in this case, unless I specify something else, this plane, the units here are in meters. If you try to draw this point, you will see you have the constant rho surface, which is a cylinder. It intersects here. This is a constant phi plane. This here, I'm just drawing this plane here. This plane is a constant phi plane. And you could see the angle that this plane makes with zx plane is pi over 3. And when these two intersect, they give you this vertical line here. So we have this vertical line which is going from the top to the bottom. This is really the intersection of the plane and the cylinder. And when you intersect this with z equal to minus 2 plane, you get your point B. So just remember here that your point B is below the xy plane. If you try to see the theta of this point, if you connect from the origin to the point B, you see that theta is greater than 90 degrees. It must be, because the point is below the xy plane, so theta is greater than 90 degrees. Of course, the position vector here in this case does not have, in spherical coordinates, the position vector doesn't have a phi component, is equal to rho a rho plus z a z. So in this case, equal to 2 square root 3 a rho minus 2 a z, minus 2 in the direction of z. In transforming from cylindrical to spherical coordinates, I will solve this one by going first through the Cartesian coordinates. I know I'm giving the cylindrical coordinates values, so I'll convert them first to Cartesian. So x, as we know, is rho cosine phi, y is rho sine phi, and z does not change between Cartesian and spherical. Phi here in this case, in this example, is pi over 3. Cosine pi over 3 is equal to 1/2. So this will give you x equal to square root of 3. Sine pi over 3 is equal to square root 3 over 2. So this will give you y is equal to 3, and z does not change. So in Cartesian coordinates, your point will have this value here. So the position vector is square root 3 in the direction of ax plus 3ay minus 2ez. In order to go to spherical coordinate systems, we have to determine r, theta, and phi. R is the distance from the origin, and we know it's equal to square root of x squared plus y squared plus z squared. X is equal to square root 3, y is equal to 3, z is equal to 2. The numbers cooperate here to give you square root of 16, so this means that r is equal to 4 meters in this case. Remember that in this example, I've shown you that the point is below the xy plane. So I'm not going to be solving for theta. I will solve for pi minus theta and then subtract to get theta in this case. So pi minus theta in this case is equal, we'll be able to find it through the triangle involving this angle. In this case, because if we take a look at the diagram we had, this is our point. This is the z-axis. This is z. So this is theta. So this angle here is pi minus theta. Okay. So if you try to draw here, you see that this is rho, and this is r. So the angle pi minus theta has a tangent of rho over r. So I'm going to be saying that pi minus theta is equal to inverse tangent of rho over r. And don't get a wrong answer here. We're actually solving for pi minus theta, not for theta, because theta is greater than 90 degrees. We know that rho is equal to 2 square root 3. This was given to us. Okay, we already know that. R we already calculated is equal to 4. We know now that the inverse tangent of this angle is equal to the inverse tangent of square root 3 over 2 here, which is equal really to pi over 3. Pi over 3 is the one that has a tangent of square root 3 over 2. So this means if you subtract, theta is equal to 2 pi over 3, and as expected, it is greater than 90 degrees because the point is below the xy plane. Now phi by definition from cylindrical coordinates, it's the same as spherical coordinates. It's inverse tangent of y over x. We already calculated y and we calculated x. Y is equal to 3 and x is equal to square root of 3. This will give you inverse tangent of square root of 3, which is again equal to pi over 3 here in this case. Okay, so in spherical coordinates, the points has three components. 4 is r, theta is 2 pi over 3 as shown here, and z is equal to pi over 3. The position vector does not include theta or phi, is simply equal to 4 r only here in this case.